Random forests. Decision trees tend to be weak learners, but that makes them ideal for bagging and boosting, and the result is what's known as a random forest. Now let's look at boosting with decision trees. Decision trees have a bad reputation and they deserve it. They're unstable, they overfit, they perform poorly. You tend to only be able to look at one feature at a time. But what about an ensemble of decision trees? In many ways, it's an ideal collection of weak learners. Because it only uses one feature at a time at each node, there is huge variety in how different trees use the features. And it's based on information gain and entropy, so in some sense it's a weak learner who's discovered the most information that it can given the limited scenario that it has to work with. Now, random forests are simply boosting with decision trees, and often we don't even use a very sophisticated boosting scheme. We do, however, tend to use bagging, bootstrap aggregation, so each tree has a unique subset of the features, and we do classification by majority vote or weighted majority vote, which is boosting, and we can extend this using pruning and parameter selection and things like that. Now, you can actually show that random forests, not decision trees themselves, but random forests collectively, are closely related to k-nearest neighbor networks. They both are what are called weighted neighborhood schemes. And so you can think of random forests as not only a successor to decision trees, but also a successor to k-nearest neighbor networks. And both can be extended using graph theory. So the random forest occupies a central position in the course for us. Now let's look at SKlearn with random forests. They're used in the same way as other classifiers. We create this classifier object, then we fit, and then we do a prediction. We do validation and testing using metrics. And the classifier object contains the trees. It's actually the estimator's underscore attribute of the classifier. Let me show you an example here, and we're going to use the iris data, and the reason is because the trees will be small. And even then they're probably going to be a little too large. So what I've got is in the notebook, I start the notebook, I import the iris data and the random forest classifier and cross-validation, that sort of thing. So here's our data. It doesn't have the target associated with it, so I'm going to put the target into the data frame. Then I'm going to do a test train split. And when I do my test train split, I see that I have my four features: petal length, sepal width, sepal and petal width and length. There's my random forest classifier fit, and then I make predictions. I can do a cross tabulation. Look how good this is. It only misclassified one in the validation set, even though this is a nonlinear classification problem. And I did so using all these decision trees. So this is in the estimator's attribute, is a list of these decision trees. Let's look at the 0th decision tree. You can see its properties there. And let's look at its graph. And lo and behold, it's an actual decision tree. And it used a whole bunch of these decision trees in a boosting type framework to come up with an excellent prediction for a nonlinear classification problem. So random forests and neural networks kind of wrap up the course here. These are the two most powerful and probably most widely used predictive modeling approaches. The support vector machines are also used very often. They're both highly interactive. You can do continuous and almost unlimited improvement, and you can combine these with other methods. Their sources of strength are their stochastic loss minimization, which we saw with the gradient descent, or the energy minimization in the Hopfield and Boltzmann. And the network topology plays a major role in both. Both can be used for unsupervised learning. You don't actually have to give them the labels. You can just give them the observations, and then they'll figure out what the best way to group all the observations is, and we'll end up with clusters and hubs similar to what we hope to get with a k-nearest neighbor network. They both can be used for regression. Just do an unsupervised learning and then just do statistical estimates over the clusters and the hubs. And you can do this also with k-nearest neighbor networks, although they don't tend to work as well. Both random forest and neural networks are multiscale. So one thing that we could look at is that networks, graphs, have spanning trees. And features at all scales can be modeled by decision trees and thus by random forests, because a spanning tree can in some sense span an entire graph if it's connected, or a small set if it has a small number of components. Similarly, the universality of an artificial neural networks means it can approximate a continuous fractal interpolation function that is non-differentiable with features at all scales. So multiscale can be produced using strong learners. So in general, every big data problem is unique. Weak learners you can design, therefore, for different scales, and then the strong learners can be built from the weak ones. So we tend to start with first approaches, much like we've done in this course, and they tend to only use small amounts of information in the data. Then we can boost, bag, add hidden layers, so on and so forth. How you're actually going to do this from the start to where you get something that you really like really depends on your problem. One thing to keep in mind is that more data beats better algorithms. Now that's not exactly true. What we actually mean by that is the goal is not to apply powerful algorithms, but to extract more and more information from the data. Let's look at what this means. So if we were doing descriptive models, the traditional modeling, we tend to think of a model as a function plus some noise. But a model as a function plus noise throws out most of the information in the data with the noise. Linear classifiers can be very good, but if there's interaction among the classes, linear classifiers tend to throw out the information about the interaction. Individual algorithms in general are designed to extract certain types of information. So more data means more information. And therefore, to wrap it up, more data is better than better algorithms. What we mean by that is that what I've given you is the tools so that you as a data scientist can extract as much information from the data as possible. But it may be just as advantageous to obtain even more data with even more information to extract. And I wish you the best of luck in doing this, becoming a data scientist in whatever form or fashion you choose. I've given you the basics. Big data is large and complex. Networks can be good models. Information is something we can measure. Algorithms optimize information extraction. And then all those algorithms, k-nearest neighbor, logistic regression, neural networks, boosting, random forest, support vector machines, and the like. You'll learn the rest by doing, because once you get started, you should be able to keep going and keep extracting more and more information, building better and better models, and becoming a better and better data scientist as you go.